Let's look at a new category of ODEs. We have already looked at systems before. They were usually linear systems. Now we're going to look at autonomous systems. So we dropped the requirement that the system must be linear, but we are again looking at a system of first-order ODEs. A system means that we're looking at multiple variables, for example, x and y, their derivative with respect to the time, and the right-hand side connects x and y. So the derivative of x depends on x and y, and the derivative of y depends on x and y as well. And they might be depending on the time as well, but if you restrict ourselves to autonomous systems, it doesn't. So their autonomous systems are first-order ODE systems with no dependency on time. For example, the ones we have seen previously, so x prime equal to y and y prime equals to minus x plus x to the third, or the variations that we have seen previously, are all autonomous systems. Autonomous systems are a bit easier than non-autonomous systems. So non-autonomous meaning that the right-hand side does depend on time. One of the easier things to do in autonomous systems is looking at singular points. The idea is that because the forcing term does not depend on time, if something has no velocity, it never has any velocity. So these points are points that do not move ever. They're called either singular points, equilibria, fixed points. They're all equivalent information to indicate a couple x0, y0, such that the right-hand side computed at this point is equal to 0. Both the derivative of x and the derivative of y need to be equal to 0 at that point. If x0, y0 is a singular point or an equilibrium or a fixed point, then xt equal to x naught and yt equal to y naught is a solution for all times. That means that solution is never going to be moving. If we want to study the behavior of an ODE in a qualitative way, finding equilibrium is definitely the step 0. And once we have an equilibrium, we can study the behavior of the system close by the equilibrium. So we know that nearby there is a point that never moves. We expect the points near it to have quite slow velocities themselves, and possibly having a behavior that is connected to the equilibrium. Because we assume the right-hand side to be continuous, that is quite reasonable. So focusing on x naught, y naught, we'll introduce capital X and capital Y. That is just a resetting in which capital X and capital Y are equal to 0 at the equilibrium. So it's just a very simple change of variables to reset around equilibrium. And if we want to be studying our system very close to the equilibrium, what we are expecting is looking at capital X and capital Y being very small. Smaller than some epsilon that is much smaller than 1. So if we study it there, then we know that the derivatives with respect to time of capital X and capital Y will also satisfy the ODE we have written with f and g that can also be Taylor expanded around x naught and y naught. So let's focus on d capital X over dt. We can expand the right-hand side as f computed at the equilibrium point, x naught, y naught, plus all the partial derivatives of f multiplied by x and y. So x df dx plus y df dy plus capital X squared over 2 d squared f over dx squared, and so forth, all the mixed terms, and so forth. But we're saying that x naught, y naught is the equilibrium, so we know that f computed at x naught, y naught is equal to 0. We are also saying that capital X and capital Y are very small. So we are expecting the square terms to be pretty much uninfluential if you're close enough to the equilibrium point. So all the terms that are involving x squared or y squared, capital X squared, capital Y squared, and the combination of capital X and capital Y are so small that they're not really gonna impact our solution. So we can rewrite our system of equations at capital X and capital Y as df dx times capital X, df dy times capital Y, dg dx capital, and so forth, where all the derivatives that I have been talking about are always computed at the equilibrium point that we're looking at, so x naught, y naught. And we can rewrite this as an ODE system, a 2x2 ODE system, because it really fits the standard setting, with our matrix being a matrix of constant coefficients. This is kind of neat because these are things we really know how to handle.